Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, let's get started. So you made it to the last lecture of the summer school. Congratulations. And now we're going to talk about georeplication in distributed systems. So the setting that we consider are a setting where we have data center distributed applications. And those could include web applications such as webmail, social networks, or online stores, as well as number crunching applications such as MapReduce. And those applications could be running across many different data centers for scalability reasons and other reasons. And oftentimes in these applications, it's extremely valuable to make sure that your data is reliable. And the data of such applications include, for example, in a web mail application, the contents of emails. In a social networking application, let's say in Facebook, the contents of your walls or your friends list, and so forth. If you have an online store, it could include the orders that you have accepted so far. Also the list of products that you're selling. So georeplication refers to, the definition of the term is replication of data across geographically distant locations or data centers. And the reason why you might want to do that is twofold. One is you might want to tolerate a disaster where an entire data center goes down because of an earthquake, for example, or because of other natural disasters. Or perhaps intermittently a data center has gone down because it has lost power. And in those cases, you'd like your application to continue working as if the data center did not have suffered such a disaster. And the other reason why you might want to do georeplication is to provide access locality. For example, in a web application, you might want to serve users from a nearby data center. So if you have a data centers in India and United States, and you're in India, you might want to be served content from a data center in India in order to reduce the latency for you to access the application. And it's known that when it comes to web applications, if the latency goes above 1 second or so, users start to getting upset. Now, the challenge in doing replication is to deal with the delays across the replicas that are in different geographic locations, and those delays can be orders of magnitude larger than delays that you observe inside a data center because of limitations of speed of light, for example. So if you think, for example, that the circumference of the Earth is about 40,000 kilometers and speed of light is 300,000 kilometers per second, and you do the calculation, then you see that it will take light 133 milliseconds to go around the Earth. And when we're talking about networks, that latency may get amplified by a factor of 2 or 3 due to the fact that you don't necessarily have straight light connections between every data center, due to the fact that speed of light inside fiber is lower than the speed of light in vacuum, and so you might lose a factor of 30% because of that. And also, inside a fiber, the light itself doesn't travel in a straight line because the light may be bouncing off the edges of the fiber itself. And so, in the end, your latency around the world for a ping might be 400 milliseconds, half a second, or even a second or so. And that is 3 orders of magnitude or more higher than the latency that you would observe inside a data center. So I'm going to explain techniques for you to provide georeplication of your data. And those techniques can be broadly divided into 2 categories: synchronous replication and asynchronous replication. And I should note that these terms are completely unrelated to the notion of a synchronous or an asynchronous system. The term synchronous or asynchronous refers to the fact of when replicas get updated when you have a write. So if you have synchronous replication, that means that your replicas get updated immediately, and the update is not acknowledged to the application until the replicas have been changed. And if you have asynchronous replication, that means that a local replica gets updated and the application is told that the update is finished, but the other replicas get updated in the background. And asynchronous replication is sometimes called also optimistic replication. I'm also going to divide the various techniques for georeplication based on the API or the storage service that the storage system provides to the application. And we're going to look at 3 different possible storage services, one of them being read-write, the second one is state machines, and the third one is transactions. So whether your storage system provides support for just reading and writing data, executing arbitrary commands in a state machine, or executing transactions. So with the read-write service, the storage service basically provides just 2 simple functions. One, to read the data given the ID of a location, and that just returns the data. And the other one, to change the data which is stored in a given location whose ID is given to a given data, and that just returns an acknowledgement. So there's only really 2 operations, read and write. Now the advantage of this API or this storage service is that it's the simplest one for you to understand. It's fairly fast and easy to implement because you don't have to worry about more powerful operations. And the minus of that is that it's fairly low level, and concurrent access may be hard to manage because of the fact that the storage system doesn't understand much about what the application really wants to do. And so when it comes to concurrent writes, the storage system is at loss as to how to handle such writes. Another possible storage service is to have a state machine, which is implemented by protocols such as Paxos and other consensus protocol. And there you can have a general operation where you can think of an operation as a function that takes the current state of the storage system, changes that to a new state, and returns an output to the user. And you can think of read and write as being special cases of that function where for read, the operation is not changing the state, so when applied to X, it remains X, and also return X to the user. In write of a given value, the operation would change the state and just return an OK to the user. So those are the 2 different functions, how you represent read and write using the general operation. And you can also think of more powerful operations such as atomically incrementing a location where the function is given X, changes the state to X plus 1, and returns an OK to the user. Or an atomic swap where you're given a new value, you get back the old value, and the state of the storage system gets changed to the new value. There's a limitation on what you can do with such general operations, which is you're limited to executing at a single location. So given a particular ID, you have to execute the function on that ID. And if you want to execute across different IDs, then you need a more general notion, the notion of a transaction. So the advantage of a state machine over just read-write service is that you have more general service here because as a special case, you can implement read and writes. But that also means it's more complicated to implement, and the function is just limited to one location. The third storage service you might have is a general transaction which bundles together many different operations. And operations could just be reads and writes, or they can be more general functions. And so this is being represented here by the fact that you have, this is just a regular expression for what you can do in a transaction, assuming that operations are just reads and writes. And so the basic idea is that you begin a transaction, you execute those operations, you end the transaction, and then you get an indication whether the transaction has committed or has aborted. If it has aborted, you can go ahead and retry the transaction. It means that all the writes that you've done in the transaction did not take place. Now in this example, I illustrated the case where the transaction has reads and writes, but in general, you could have arbitrary functions. It's often not necessary to have arbitrary functions inside transactions because those functions can be implemented with reads and writes. And in this box, I showed the template of how to do that. But for example, if you wanted to have the arbitrary function operation to be an atomic increment, you can have a transaction that just reads the data, computes the value which is 1 larger, and then writes the data and commits the transaction. So you can express the atomic increment as a read and a write. And because it's bundled together in a transaction, you don't have to worry about the fact that individual read and write themselves are not atomic. So the advantage of a transaction service is that it's very powerful. And in fact, it's the most general service of all because I just showed you that you can implement state machines using transactions. But the drawback is it's harder to implement and it could be less efficient. Now, there are other services for, or APIs for storage and systems. Some people talk about a block storage system, for example, and that would be a special case of a read-write service. So a block service, you can think of that as being a disk where you have a bunch of different sectors or blocks and you can write a fixed length quantity on a given sector. Well, we can think that as just being special cases of a read-write service where the set of IDs is the interval from 0 to n-1, where n is the number of blocks that you have in your service. Another possible storage service is that of a file, where you can have file operations to create directories and rename files and remove directories, list the contents of directories, and you can think of that as being as a special case of a state machine. And so we're not going to consider these two other servers, we're just going to consider the three ones that I mentioned before. And so today I'm going to go through various different techniques that you can use to achieve georeplication. And this table shows two different axes. One is whether you're doing synchronous or asynchronous replication. And the other one is what type of service that you would like to provide to the application, whether it's read-write, state machine, or transactions. And so we're going to cover all these techniques. Let's start with synchronous replication, the techniques that were under the first row, because those are the simplest ones. And let's look at the first column, which was that of a read-write service, and think about how we might implement a read-write service. Well, one simple scheme is for you, whenever you have to write to a given location, you just write to all replicas. And when you read, you just read from the local replica, the replica that is closest to you. And if you implement a scheme like this, the reads are going to be fairly fast because you don't have to go over the wide area to retrieve your data, but the writes are fairly slow. And in addition to that, your writes will block if you're not able to achieve to contact one of the replicas, because you have to wait for all the replicas to acknowledge your write. There's also an issue with concurrent writes. Even with this very simple scheme, there's an issue where if you have two different parties trying to write at the same time, if you're not careful about the order in which you're accepting those updates at the replicas, you may end up in a state where the replicas diverge. And this shows an example here where we have two clients executing writes on the location X for a value of 10 or 20. And it so happens that the first replica receives the first write before the second one, and the second one receives the second write before the first one. And so the replicas end up with different values for location X. So one way to solve this problem of concurrent writes is to have a primary replica that orders all the writes and determines the order in which the replicas have to accept the writes. And another solution that you might consider is to use a timestamp to order the write. So when a write occurs, it gets assigned a timestamp. And there are several different ways in which you can assign timestamps. I'm going to talk about that later. But you assign a timestamp to a write, and then the replicas are supposed to accept the writes and incorporate the writes in the timestamp order which is given. And so if a replica receives a write with a smaller timestamp than the one that it has currently stored, then the replica just ignores this. And in this slide, you can see how we can avoid the problem where the replicas have diverged by using those timestamps. But you can see that even in the simplest case where you just have a very simple read from one, write to all, you have to be already careful about concurrency. And in the other possible approaches for georeplication, you see that things get substantially more complicated. So here's another possibility. Had a question?
Then how the timestamps will work for different processes, like they are not at all synchronized kind of. Then how will get the global timestamps for all the replicas?
Yeah, I'll talk about getting timestamps soon, but you could have, for example, clocks that are approximately synchronized across data centers, and when you get timestamps, they are close to each other. You can just use timestamps that are sequence numbers. And I would say that if you're running a data center that is geo-distributed and you have fairly reliable links connecting them, and sometimes the links are congested and so the latency goes up to the roof, getting synchronized or approximately synchronized clocks is not too bad. And so this is the approach that I would advise for getting such timestamps, but there are other ways of doing that. And so I'm going to describe that, I think, in one slide or two, in fact on this slide, on how to get timestamps for the write quorum, but you can use the same timestamps for the other scheme. So instead of writing to all and reading from one, you can think of a scheme where you write to a majority or you write to a quorum and you read from a majority as well. And if you think about the scheme you get to a situation where both writes and reads are slow, because you cannot execute writes locally, you cannot execute reads locally. You have to go to the wide area, you have to go to a remote replica to execute both operations. And so why would you ever think about using such a scheme? And the reason is that this scheme would be non-blocking under failures. And in particular, if you have a remote data center which is temporarily unreachable because, for example, of congestion in the links across data centers, this scheme would allow both your reads and writes to continue, even if a majority of such replicas are unreachable, without having to block. Whereas if you're doing write all and read one, the reads are super fast, but the writes would block even if one replica or one data center becomes unreachable. And if you have a large number of data centers, and you can think of a large being more than like 10 or 20, then having a scheme that requires all of them to be reachable and timely reachable wouldn't be very practical. And so you might want to go for a scheme that uses quorum instead. Now, here you also have to worry about concurrent writes being issued, and you can use timestamps to do that, just like in the previous, to ensure that the replicas converge, just as I explained to you in the previous slide. You should not use the primary replica to order your writes, unlike what you could do in the previous scheme, because if you did that, then you lose the advantage of not having to block your system when one of the replicas is unreachable. In particular, if the primary replica, if you choose to have a primary replica to order your writes, and that replica is unreachable, then you just lost your advantage of using quorums. Now, you do have another problem that you don't have when you write to all and you read from one, which is that of oscillating reads. And this problem occurs when you have two reads that are executing, and you have multiple reads executing, and they're oscillating between one new value and one old value that was previously written. And so this shows an example where we have three replicas, and let's say the first and the second replicas, or the second and the third replicas, store the value 10 with a timestamp of 1, and the first replica stores a value of 20 with a timestamp of 2. You notice that the value of 20 with a timestamp of 2 is not stored in the majority of replicas just yet. And the reason for this is because the write of 20 with timestamp 2 is still going on. So eventually, it's going to be stored in a majority of replicas, but so far it's not stored in a majority just yet. And if you look at what will happen if you try to read in such cases, the read will collect replies from a majority of replicas and will return the one with the highest timestamp. Well, if the first read reads from the first and the second replicas, then it will return the value of 20 because 20 has a timestamp of 2. If a second read comes and reads from the second and the third replicas, well, both of the replicas have the timestamp of 1, and so the second read will return a value of 10. And now the third read comes and touches replicas 1 and 2, and so returns a value of 20. And the fourth read comes and goes to replicas 2 and 3, returns a timestamp of 10. So you can see that in each case, the reads is going to a majority, but it's going to a different majority. And because the value 20 only appears as a minority, you have a situation where your reads are oscillating between two different values. That implies, for example, that this implementation does not satisfy linearizability, because linearizability will require your writes to appear to execute at an instant point in time. And if your reads are oscillating between two different values, that means that your write is happening at many different points in time. And if you want to avoid such oscillating reads, there's a question.
Yeah, so why not do it this way? Read from a quorum, read from a particular number of replicas, and then pick one which is because they are having version numbers here too. So why don't we pick the latest version after reading from a quorum?
Yeah, so well, the second read, which again is picking the one which has the highest timestamp, right? But it so happens that the one that has a timestamp has a value of 10. And this read could be being executed by a different client. And so the first client, for example, can go and read and get a value of 20. Second client comes, and the first client may send a message to the second client saying, look, I saw 20. And then the second client comes, reads a value of 10, and sends a message to a third client. Third client goes and reads and gets the value of 20, and so forth. And so this read is oscillating despite the fact that there was only a single writing to the system, right? So the solution that you propose would work, for example, if you had a single client executing multiple different operations. The client can remember what was the highest timestamp that I ever returned for that particular location, assuming the client has enough space to store the information. Next time the client comes and reads, it can just return the data. Assume if the replicas have data which has a timestamp smaller than that. So if you want to avoid the problem of oscillating reads, what you can do is to have your read operation write back the value that is reading to a majority of replicas. And it doesn't have to be the same majority that it read from. And so in this case, if you recall, we had a read that would return a value of 10 because it went to replicas 2 and 3. Sorry, we had a read that returned a value of 20 because it went to replicas 1 and 2. And the value 20 was stored only at a minority of replicas, potentially, as far as the read was concerned. And so what the read will do is realize that it's possible that the value of 20 with timestamp of 2 is not yet stored in the majority of replicas, in fact, because it only saw this in replica 1, and go back and write back that value with exactly the same stamp at the majority of replicas. And you can prove that if you do this, if you have this write-back phase, if reads can write back values and execute that phase, then you get linearizability, and you don't have the problem of oscillating reads. Now, another issue that comes is how do you obtain the timestamp when you're writing a new value, because you have to obtain a new timestamp to do that. And the simple, most practical way of you to do that is just to rely on synchronized clocks or closely synchronized clocks. And I believe that in a setting where you have multiple data centers, which is mostly connected to each other most of the time, you could get such synchronized clocks by using standard protocols such as the network time protocol or variants thereof. It doesn't necessarily ensure that all the clocks will be perfectly synchronized. There can be a small drift, especially if you have periods of time when you don't talk from, when one data center cannot talk to another because of congestion or other reasons. But even if they are approximately synchronized, that would be good enough. Now, if you don't want to make that assumption that you have synchronized clocks, then you can also get your timestamp from a majority of replicas. You need to get a new timestamp. You ask a majority of replicas, what is your current timestamp? They return a value, pick the max, you add one, and you pick that to be your new timestamp. And that will add one communication round trip to your protocol. Rather than that, and if you think about what's going on here, is that you're trying to implement yourself a very weak form of clock synchronization by going to these replicas and trying to get the value of the clocks and adding one yourself. You might as well rely on a clock synchronization protocol to do that work for you. Now, I'm not saying that this is a good thing to do in every setting if you have disconnected operations, and you may not want to assume that you have synchronized clocks, but in a data center setting, in a geo-distributed data center setting, that assumption may be quite reasonable. So I was addressing the first column of where you wanted to implement a read-write service. Now I'm going to address the second column where you want to implement a more powerful state machine service. And I think people have covered that before. So the state machine approach, you have replicas that are initially at the same state, and you have to ensure that replicas agree on the kth input or the kth operation to apply. And assuming that operations are deterministic, if the replicas agree on what that operation is, they apply that operation, they end up in the same state. And the mechanism, or the tool that is used to agree on the kth operation is a consensus algorithm, which could be, for example, the Praxis protocol that is able to tolerate crash failures of up to a minority of processes. There are other consensus protocols out there. Most people in systems that are out there use Praxis, but there are other possibilities, such as the Chandra-Intuig algorithm and others. Also tolerates a minority of crash failures, or you can use protocols that are able to tolerate Byzantine failures as well. So this has been, I think, covered previously, so I'm not going to go into much detail of how these algorithms work. So rather, I'm going to look at the third service that you might want to provide, which is that of a transaction. That was the most general service that you have for a storage system. And still looking at the case of synchronous replication. And the traditional approach for you to implement transactions is to acquire locks during execution or during commits. And Liuba talked about that. That would be pessimistic concurrency control or optimistic concurrency control, depending on when you're acquiring the locks. And you can, if you have a geo-distributed setting, you can think of a setting where the locks themselves, you need to implement them, but they're implemented by a distributed lock service. And the commit itself could be implemented by two-phase commit. And there are other possibilities, but that's the simplest thing you can do. And the issue that may come here is that you need to acquire those locks either when you execute a transaction or when you try to commit a transaction, and the distributed lock service may be slow because you need to acquire those locks over the wide area. So another possibility to implement a transaction service is to use what is called deferred update replication. And the basic idea here, and there are a lot of bullets on this slide, but the basic idea is that you execute a transaction locally on a replica. And you can, transaction is reading data, you just return the data locally. Transaction writes data, you buffer those writes, and you don't necessarily send those writes to the other replica just yet. And when it comes the time to commit a transaction, you use an atomic broadcast protocol that ships the entire transaction to all the replicas. Now, an atomic broadcast protocol, it's also called a totally ordered broadcast protocol, ensures that all the replicas will deliver the same set of messages in exactly the same order. So you broadcast the transaction, that ensures the other replicas will receive, deliver those transactions. And there might be many people broadcasting transactions at the same time. But all the replicas will deliver the transactions in exactly the same order. And when a replica delivers a transaction, there was a bunch of reads there, there was a bunch of writes there. So what the replica does is to check whether the reads return the correct result, because recall that the reads were executed against a local replica, but when you deliver the value that the replica has may have changed in the meantime. And so you just check to see that the values that are read are correct values, and then you apply, and if that's the case, you go ahead and apply the values that you have written. There's a question here.
What happens in case of concurrent broadcast?
The case of what broadcast?
Concurrent broadcast at the same time happening.
So yeah, let's say that you have two transactions executing, one in data center in the United States and the other one in data center in India, right? And let's say that those transactions are trying to implement an atomic increment of a given location, location X. An atomic increment means a transaction has two operations. One is to read the content of X, and the other one is to write the content which is one higher. And they're both trying to do the same thing. And let's say also the transaction is going to return the value that it read to the application, so the application can go ahead and do something with this, right? Now, it's clear that those transactions are conflicting, and you will not be able to execute both transactions at the same time running locally. Let's suppose that X is initially 0. So both transactions will read 0 from X and will write 1 to X. Now, how is that going to work, right? So when the transaction has finished executing, it will atomically broadcast, the system will atomically broadcast T1 and T2. In the system, atomic broadcast ensures that all the replicas are going to deliver these two transactions in the same order, all replicas. And so either all replicas deliver T1 before T2 or vice versa. Let's say T1 before T2. When you deliver T1 before T2, now you have to validate that T1 really executed in the right way. And the way you validate this is by checking that the values that T1 read correspond to the value that the replica currently has. Now, the replica currently has X equals 0, so the value of X equals 0 is the correct value to be read, and the right of X equals 1 just go ahead. So when that happens, T1 gets committed, and the replica says, okay, T1 has committed. And the application also is doing exactly. So the application is running at one of the replicas. Eventually, that message will get delivered to the replica where the application is executing. And when the message gets executed, the system will see whether the reads are consistent. Then it will tell the application, yes, the transaction committed. In the case of T1, it will have committed. Now, when you go and deliver T2, T2 has read X equals 1. But unfortunately, so it has read X equals 0. But unfortunately, the other transaction has already changed X from 0 to 1. And so that's transaction will abort. There's one optimization which is important for deferred update replication, which is that if your transaction has no writes, so it's just reading stuff, then there's no need to atomically broadcast it, and there's no need to actually validate it. You can just execute a transaction against the local replica, and then it's done. And the reason why this is allowed is because if you execute it against the local replica, you still ensure serializability. You may have to serialize the transaction in the past because the local replica may not have yet all the transactions that have been atomically broadcast and so forth, but it's still going to be some state in the past and it's going to be serializable. So you can do that if the transaction is read-only. And it turns out that optimization is quite important because in many applications, you have lots of read-only transactions. Now, the issue with deferred update replication is that the performance of the system is going to be limited by the performance of your atomic broadcast protocol. And if you look under the hood of what's happening inside the atomic broadcast protocol, it's really solving consensus. Because it has to uniquely agree on what is the kth message which is going to be delivered in a total order to all the replicas, and that is the problem of consensus. And so the performance of such system, even though it might be better than the performance of the traditional system, because the synchronization, the coordination is only happening at the commit time, may still suffer because of those delays over the wide area. So I covered the case of synchronous replication, and now I'm going to cover the second row of the table, which, let me just move ahead here just to show the table, which is that of asynchronous replication. And for asynchronous replication, I'm going to cover the case of read-write, state machine, and transactions as well. So, but before I do that, any questions about synchronous replication? Okay, in that case, let's move on then. I had an animation here. Okay, so basically the idea of asynchronous replication or optimistic replication is that an operation executes on a local replica, and again, the control returns to the application saying the operation has finished, but the reality is that that's a lie. The operation has not yet been applied at all the replicas that happens in the background. I should first notice that once you move to asynchronous replication, you may be subject to data loss because the application may get a notification that the operation has completed. The operation may have been applied only to the local replica. If you have a disaster that destroys the entire data center, including the local replica, you may not be able to retrieve the data unless, of course, the local replica recovers that the application has gotten acknowledgement from. So the application said the operation completed, but then the data gets lost because the replica goes away. And one key issue, and we saw that a little bit with Mike's presentation, is that you may have the issue of concurrent updates that you have to deal with. And that was true even for the case of synchronous replication, but for the case of asynchronous replication, this is even worse because you have already told the application that the operation has completed to some extent. And in reality, later on, you may realize that that write was concurrent with another write, and you may have to deal with a situation which may be in ways that are unpleasant to the application. And you have several options of how to deal with this issue of concurrent writes. One of them, the simplest solution, is just designate one of the replicas as being the primary copy and say this is the only place where you can change your data, and that's called primary copy replication. And I'm going to talk in more details about each one of these possibilities. The other one is to prioritize one of the replicas where the updates can happen faster than in the other replicas, whereas in the other replicas the updates would require wide area communication, and that's called preferred copy. You can also have techniques whereby you will throw away some of the writes by, for example, looking at the timestamp and deciding that the smaller timestamp write will be discarded. The application may or may not be happy with that. Or techniques that combine the updates of these concurrent writes by using merges of history, reordering of history, or if you're using operations that are commutative, then there's the combination is easy. There was a question here? Okay. And so we're going to be covering these techniques. You'll notice that each one of the columns in the second row has some common items. So you see that primary copy, for example, appears at several different places here. Let me get this thing started. Primary copy, primary copy, primary copy. And so I'm going sometimes to be talking about a technique and saying, oh, this is the same as in the other, as for the other interfaces. Let's start with read-writes, primary copy, which is the simplest one. The basic idea is that you designate one replica as being the primary copy. Writes are only allowed there. The other replicas, you can still do reads there, and that's okay. And if you're doing reads at other replicas other than the primary, you may return stale versions of the data. But even though that might be the case, you would still satisfy sequential consistency, which is this condition that we've already seen before. But basically it says that operations appear to execute as a sequence that respects the order in which the operations were locally submitted by each one of the processes. And I have an example of here of what sequential consistency means, but I'm not going to go through it because I think we covered that material already. But this example, if you want to look at the slides later, has 4 operations, and it shows that there's a global order that respects the local order and that explains the execution of the 4 operations.
What's the significance of making a primary copy then, if we are reading from anywhere?
Well, the primary copy is for updating, and so this is the only place where you update. For example, you may designate India as being the only place where you update your data, and if you're running a web application, you travel to the United States, then you need to ship your updates to India before the updates can be completed, and then once it completes in India, you get back the acknowledgement and you're done. And so the primary replica is used for restricting where you can update the data.
And it is also a bottleneck then?
Well, there's a problem of perhaps being a bottleneck, but there's also a bigger problem of latency, right? So, and especially for web applications, you have to ship your updates to a possibly distant data center. And so this approach, I'm not going to claim that it's the best one, it's just the simplest one. Restrict your updates to a single place. Life is easy, but there are some performance implications of doing that. Now, if you don't want to restrict your updates to a single replica, you can allow your updates to occur at all replicas. And then you can use this technique also called Thomas Wright rule, or last time temp wins. And the basic idea is that a write obtains a timestamp that can be from a clock or it can be through other means. And when the data gets copied in the background to a remote replica, writes that have a higher timestamp obliterate writes that have a lower timestamp, But if you're trying to copy over a write that has a lower timestamp and the remote replica already has a write with a higher timestamp, you just discard the one that has a lower timestamp. So this is similar to what we're doing with a quorum writes or writes to all and so forth. But the difference here when you have a synchronous replication is that these things are being done in the background. So the application has already gotten an acknowledgement that your write has completed. But then it may turn out to be the case that it got assigned a small timestamp, it got copied to the other data center and gets overwritten by the other writes, and the write will all of a sudden disappear. Well, let me point out that you still have the semantics of sequential consistency if you do something like that. But this scheme may actually lose data. The application gets an acknowledgement that the operation was completed, but the operation later on disappears. You can have concurrent writes. And so one way to avoid this problem is to use history merge. And the basic idea is to detect the fact that you have concurrent writes and then to invoke an application-specific function that will look at all these concurrent writes and decide what the result should be, how to combine those writes. And the rule can be just pick the one that has the high timestamp, and that would make this a special case of the previous scheme that I proposed, which is Thomas Wright's rule. Or it can be something more complicated, which is to look at the value of the writes, for example, and consider that in the context of a given application. For example, if you have a calendar application, you may realize that the writes are writing to perhaps entries in your calendar that are not necessarily inconsistent with each other. You may decide that both of these writes can go through. But the point here is that the merging function needs to use semantics of the application in order to combine the value of the writes. And so you need to do these two things. One is to detect the concurrent writes, and the other one is to merge the writes. And as we have seen from Mike's lecture, that we can use vector timestamps to detect concurrent writes. And the idea, and there are different ways of embodying or constructing such vector timestamps, but the simplest way is to have in the vector one entry per replica, where the entry of a local replica represents the local timestamp of the operation, and the entry of the other replicas represents the number or the timestamp of the largest operation that you have ingested from the other replica. And so I think this is kind of a mouthful, so it's better understood by an example here, where we have two replicas, and in the first case we don't have any concurrent writes, so we have first a write of on location A of value of 1, and that write receives a vector timestamp of 1, 0. The 1 represents the fact that this is the local timestamp that this write is receiving, and that timestamp is going to be 1, 2, 3, 4, and so forth. It's monotonically increasing for each operation. And the 0 represents the fact that this replica so far has seen 0 other writes from the other replica. And so when these operations get copied to the other data center, so here you have another write of A of 2 that happens with a timestamp 2 of 1, then you can see that these writes are not concurrent with each other because of the fact that this vector timestamp is strictly bigger in the partial order of vector timestamps than the other two. So you know that these writes, none of these writes are concurrent with each other. It's a question.
This still requires the communication between these two replicas to know about the timestamp of this. If there is no communication at all, so how to ensure in that case?
Oh, so this is a case where the communication between the replica gets delayed. But
Replica 2 knows about replica 1 that is the timestamp is 2. If there is a communication between replica 1 and 2, like how to ensure in that case that there is a communication between these two?
Are you talking about a communication being done by an application which is not the application that is executing the protocol, or are you talking about communication that's happening in the network sending messages of the replication protocol itself? Which, when you say communication, do you mean an application communicating with another that has nothing to do with the system that we're implementing, or you're talking about a communication of the system that we're trying to implement?
The replica actually learns from another replica about the latest timestamp of another replica. For example, here replica 1 is 2, 0, and the replica 2 in the another one is 2, 1.
Yeah.
So like if there is a communication, then only another replica knows that what is the timestamp of the
If there's a communication, then what? I missed what you said after that. Then you can only pick one?
So that means in concurrent, right? There has to be communication between these two replicas.
So speak louder. If there's a communication, which there is one communication here because this value is being propagated, right?
For example, in concurrent writes, for example, if we want to make sure that there is a linear eligibility, so there has to be a communication between these two replicas.
Right, so we're not going to assure linearizability here. We're just going to assure sequential consistency or something. In fact, when we're dealing with concurrent writes and merging histories, we're not even going to ensure sequential consistency. And so the kind of guarantees that you can have when you have a synchronous replication are significantly weaker than when you have the synchronous case. You may be able to settle with things such as causal ordering and so forth. Or if you have a single primary replica, you may be able to get sequential consistency. But in general, we're not going to get strong properties at all out of a synchronous replication. So here's another case where we have concurrent writes. And the reason why those writes are concurrent is because the update of the writing of A to 1 got propagated to the second replica. And it took a long time to do so. In the meantime, the second replica has received a write on value A, on location A for value 2. And you can see that those writes are concurrent because this write receives a vector timestamp of 0, 1, 0, meaning that at this point, the replica has seen 0 updates from the other replica, and 1 being the local timestamp that the write gets assigned. And so all I'm saying here is that if you want to detect concurrent writes, you can use vector timestamps to do so. And there are variants of vector timestamps where you have more fine-grained timestamps, and you have a counter for each object, for example, or for each group of objects, and you're keeping a vector for that. This is the simplest case where you just have one entry per replica or per data center as opposed to one entry per object or per group of objects per data center. But just mention that there are some variants of vector timestamps that can give you some stronger properties or some better ways to detect concurrent writes. But once you detected that a write is concurrent, you need to merge the concurrent writes, and for that you need the application-specific merge function. And in the example that I gave before, when the write of A for value 1 arrives here, then the system will realize that this vector timestamp is comparable to that one. There's been a concurrent writes, and the merge function will take the value of both of these writes and decide what should the new value for location X be. And so, and as the application writer using such a system, you have to provide such merge function. And in certain domains, the merge function may be easy to devise, or you may design a merge function that uses, for example, the largest timestamp to do that. But in general, devising merge functions is not very easy. Let me also point out that when you're devising a merge function, you have to ensure that the replicas eventually converge. And so, in particular, when write of A of 1 arrives here, you call the merge function to merge this write of A of the write of A of 2 with the write of A of 1. But when this write goes here you also call the merge function in order to merge together the updates of A equals 2 with the updates of A equals 1. And both of these invocations of the merge function have to ensure that the final result is exactly the same. And it's easy to see perhaps in an example where you have two writes, that merging two writes might be easy. But in general, if you have k data centers, and you may have a situation where you have to merge multiple up to k different concurrent writes. And you have to ensure that in the end, and things can get merged in orders that are not intuitive. And for example, the first and the second write may arrive at the third replica, but the first write may arrive at the fourth replica without the second writes. And all of these things are executing merge functions. In the end, you have to ensure that the merge functions converge to the same state. Otherwise, the replicas will diverge. Question? Okay, can you speak louder because I can't hear you? Sorry. From 0, 1 to replica 1. Well, so the reason why this arrow is going this way is because you have an application sitting here. Application is sitting on the second data center running on replica 2, and the application has decided that it wants to write a value. It wrote a value A equals 2. And now it got an acknowledgement from the system saying, yes, it's been written. And now the system is taking care of replicating that value in the background and sending that to the other side. And so this arrow representing the sending of the value that now 2 has been written to A to the other replica. And so, and this arrow could be fast or it could be slow, and depends on what is the current traffic and what is the current communication delays across the various data centers. And so here I'm just illustrating different examples. So this thing took a long time to replicate in the background. In the previous example, this took a short time, but over here, this thing just executed very quickly.
So are you saying that in this case, what replicator 2 writes own copy, and then later on this signal comes from replicator 1, so we have to merge two times, one replicator 2 as well as.
In this example, yes, but one of the merges is fairly easy due to the fact that you're trying to merge a write of A on 2 and a write of B to 1, and A and B are different locations.
But replica 1, you are writing A1, right? And in replica 2 also somebody is.
So you only have to merge once in each data center in this case, and the reason being that you only have one write to A here, one write to A there. So you have a.
So is the question, so are you saying that there is a merge that has to occur on replica 1 and a merge that has to occur on replica 2? That's what you're saying. So
Right.
anytime there is going to be a merge in each data center, that's what you're saying.
Yeah, that's right, and you have to ensure that.
You are environment again.
All right, and that's exactly true then. You need to have a merge executed at each one of the data centers, and not only that, you have to ensure that the merge converges to the same state once all the operations have finished. And the responsibility for making sure that happens is the application provider that provides the merge function. Yeah, so coming up with merge function is not easy. And in the context of limited domains, and for example, if you have a calendar application or if you have an email application, then the merge function might be obvious. For example, if you're, let's say, have one update to your email was to mark the email as being read, and the second one is to delete the email, then you decide that the merge of this should really be to delete the email. And so if you look at restricted domains, then you can write merge functions, and sometimes it could be quite easy. But in general, the merge function is not easy to come up with. So moving on here for the case of second column of the second row of the table, which was that of, suppose that we have now not just a read-write service, but a state machine service where you can have these arbitrary functions being applied to your data. Well, if you want to do just primary copy, which was the simplest of all the schemes for asynchronous replication, what you can do is exactly the same as you did for read-write case, except that you're going to treat as a read operation any operation that doesn't change your state. Now recall that your operation was specified by this function that given a state returns a new state and some results. And a read operation is going to be defined as a function where the new state is equal to the old state, and the response can be, for example, the state, or it can be some computation being done over the state. The computation could be, for example, if your state is extremely large, it could be a row of a table. It can just be extracting one of the columns of that row. And you get sequential consistency if you do that. Now, this is perhaps slightly more interesting. When you're designing a state machine, you can choose what are the operations that you want to have available for your application. And if it so happens that all your applications are commutative, and by commutative it means that the update that they perform can be performed in any order regardless of the number and the order in which these operations are occurring, then things get easier. And so this is being shown, let's say, two operations F and G. And again, these operations are defined by two components, one in which is changing the state and the other one which is returning the value to the user. When I say the operations are commutative, I just mean that the first component of F1, of F and G commutes. So the first components of F and G commute with each other, which is being written here. This is function composition. So if you have such commutative operations, then you allow each replica to have its own ordering of operations. And because the operations commute, the replicas will converge. So really what I'm saying here is that you can use the merge approach that I explained before, where really the merge function is a function that doesn't do anything because of the fact that your operations commute with each other. So one example of that would be like an atomic increment. I think that's an example that came in Uberstock. And so if you have two different atomic increments being executed over the same object, then it doesn't really matter the order in which you apply such atomic increments. And so the function that merges will be the function that doesn't do anything. So there are Now, the more general case of how to merge histories when you have a state machine is also similar to that of merging when you have a read-write services, but there are two important differences. So the first difference is that the merge function becomes even more complicated because the application needs to tell you how to merge every possible interleaving of executions of every possible operation that you can execute by the application. So what I'm saying here is that operations are not just writes that you need to merge or reads, but they can be atomic increments, or if you have an application that has semantics at a higher level, for example, a calendaring application or a web email application, like a web email application might be to delete an email, or it might be to mark a message as being read. The application has to provide the merge function for all those functions that the application is using. So the second difference is that if you recall with the state machine, you can do two things with an operation. One of them is to change the current states, and the other one is to return a value to the application. And if you have some operation, for example, don't change the state and just return the value to the application. Other operations just change the state and return an OK to the application. But you can have an operation that does both of them. For example, swap operation, change the state and returns the old value. Change the state to a new given value and returns the old value. And so the second component, which is the value which is being returned to the application, is not going to be dealt with by the merge function. And the reason for this is because it's too late to do this. So the application has already submitted the operation, it has executed the operation locally at a replica, and it has gotten back the result of the operation, which is the second component in the operation being applied. And the application has moved on to do different things. And so even if you have a merge function that will ensure that the states of different replicas converge, the value that the application already got in the past is something which you cannot fix. Well, there would be a way to fix this would be to allow the application later on to ask what is the new value that I would have gotten after the merge function was applied. And this, to some extent, leads to the next approach, which is that of the history reorder. Oh, let me just point out that I've been perhaps giving the impression that the merge function is extremely hard to come by, and it is indeed difficult in general, but as I mentioned before, there are limited domains where it's possible to come up with reasonable merge functions such as calendaring applications, email applications, and perhaps others. So the other way for you to handle concurrent writes when you have a state machine is to reorder your history or to revise history. And the basic idea is that an operation is initially assigned a tentative ordering. And initially, by that I mean when the application submits the operation, at that time the operation is assigned a tentative ordering, but this ordering may later on get changed. And eventually, the operation receives a final or stable ordering. And at that point, the application may get a notification saying, now, finally, the ordering of application has been established. And let me show you how that works with an example with 3 replicas, 1, 2, and 3. And what I've shown here is that there are certain operations that are colored green, and these are the stable operations. And what that means is that the operations initially got submitted. It got initially a tentative ordering, but after a while, the system has decided that the operation has been replicated, or the system has gone through some coordination mechanism that determines a final ordering for this operation. And once the final ordering has been determined, this ordering is not going to change, and this ordering is going to be exactly the same at all the replicas. And so this is showing the fact that replicas 1, 2, and 3 have applied 4 green operations, and they have applied those operations in exactly the same order. But you can also have operations that are only tentatively ordered at each one of these replicas. In the case of replica 1, we have 2 blue squares here. So these are operations that have received the tentative ordering of being, in this case, the 5th operation or the 6th operation in the ordering. What's going to happen is that later on, the system is going to pick a next operation to make it a stable operation. And let's suppose that it picks this blue operation. And it's going to make that to be the stable order, the final ordering that the operation will receive. And when that happens, this operation will get propagated to the other replicas. It will become the 5th operation in the stable orderings. And this operation that used to be, for example, this red operation that used to be the 5th one in the ordering will get pushed forward and will get reordered to be now the 6th operation. So this operation, that was the blue operation, just got inserted here. And that's what I mean by revising history. And so the application has to be written in a way that it's ready to deal with things like this. And so initially the application calls the system to execute the operation. It gets back an OK, gets back a response. But it has to realize that's only a tentative ordering. Later on, it receives an indication that the stable ordering has been achieved, and then the application can decide to perhaps change some of the things that it's done in the past as a result of receiving that notification. Okay, so in the 4 minutes that I have left, let me briefly talk about the third type of service in a synchronous for asynchronous application, which is that of executing transactions. And you can also execute transactions by assigning a primary copy as being the only replica that can modify the transaction. And that is similar to some sense as to having a state machine with a primary copy. There are some complications that you may have in-flight transactions that may require you to abort transactions or to keep multiple versions of objects in order to execute such transactions. I won't go into the details here, but let me talk about something, because primary copy, it's not extremely interesting, especially because, well, it may be interesting if you can find a way to assign a primary copy where all the updates happen, but in many of these web applications, for example, in a social networking application, there might not be a way for you to assign a primary copy, but there might be a way for you to assign a preferred copy, which is this other technique, where we assign each data item to a preferred replica. And the rule is that you can change the value at any of the replicas, and so it's not as restrictive as the primary copy approach. But if you try to change it at the preferred replica, it's going to be faster than if you try to change it elsewhere. And in particular, if you try to change it at the preferred replica, the change is going to happen only with local communication without having to go to the wide area. Whereas if you change it at other replicas, then you're going to have to pay the price of coordinating with the location where the preferred replica is. And so in a setting like this, when you have a preferred copy, you can execute on a transaction reads and writes operation always on a local replica. And the reason you can do writes on a local replica is because only on commit time you're going to be coordinating with other replicas to see if there are any issues of conflicts. If you're trying to commit a transaction that has only read data, you can also execute that against a local replica. And if you're trying to commit a transaction that has modified data, well, if it happens to be the case that all the items that were modified by the transaction have a preferred replica that is equal to the local replica, then the commit of the transaction can also happen locally without any remote communication. But if the transaction has changed even one item, which is not, whose preferred replica is not the local replica, then the transaction would have, the commit of the transaction would have to incur communication to proceed. So this shows some examples of having preferred replicas executing transactions at the same time, but I have about a minute left. So instead of going to the low-level details of this, let me just tell you about some takeaway lessons here. So I would also mention that you can also do history merge, and you can also do the other techniques that which one was the other technique? Was history reorder for transactions, and the techniques for doing so are similar. You rely on the application to provide a function that will, in the case of history merges, merge the various conflicts or the concurrent transactions that we've seen so far. In the case of history reorder, you rely on the fact that applications can be getting back this message saying the order of your operation has changed. And so in this method, basically, you're moving the burden of resolving or dealing with concurrent updates to the application. So to conclude, georeplication is an important problem today in the context of web applications, because we like to provide disaster tolerance where a data center goes down, but the application continues to function. And we also like to provide access locality so that in the context of a web application, for example, users can be served from a data center which is local to the user, as opposed to having to serve a user from another continent. From what I hear, for example, in Facebook, if you're not in the United States, you're going to be served by a data center which is either in the east or the west coast of the United States. And a few years ago, it used to be the case that all the users, even in the United States, would be served off from a single data center in the west coast. But that would increase the latency of users that are not close to that data center which is serving all the updates. And so I presented several mechanisms for you to geo-replicate your data, and they're broadly divided into two ways, synchronous or asynchronous. And the synchronous will ensure that the replicas are updated before acknowledging to the application that the updating has finished. And asynchronous, the updates happen in the background. we also looked at several different types of services, read-writes, state machines, or transactions. And there's really no single best scheme. These various schemes provide a trade-off between the power of the service that you provide, whether it's read-write, state machines, or transactions, how complicated it is to implement these things. Implementing transactions is much harder than implementing state machine or implementing a read-write service. But there's also, when you move from synchronous to asynchronous replication, the trade-off of moving to a weaker consistency when you have asynchronous replication. Using such a system that have asynchronous replication is more complicated because there are burdens often in replication of dealing with conflicts. The complexity when you move to asynchronous replication also increases, but as a trade-off for all of these bad things, you get much better performance. And with that, I would just say that if you can use the simplest scheme that is available to use, synchronous replication, if paying the cost of having to go to remote replicas of few hundreds of milliseconds is too much for you, then you have to move to asynchronous replication and you have to choose the technique carefully. And with that, I'll conclude and I'll take a few questions. Thank you. Yes.
In a general sense, do the data centers exploit the geolocation mechanisms? Do they exploit diurnal patterns arising due to usage, due to time zone differences? So for example, in the United States, the Facebook would be used during the night time, for instance. So you don't really have to replicate it immediately. So is there any adaptive scheme that is employed for such cases?
Yeah, well, one can imagine doing that. I mean, these diurnal patterns are used for several different things. In the context of replication, oftentimes you have requirements that if you have a disaster, for example, you don't lose more than 15 minutes of data. And in the case of Azure, for example, it ensures that if you write to one replica, you get replicated within 15 minutes to another replica. And that's, if you think of window of vulnerability of 15 minutes, if you have a disaster, it tends to be smaller than the diurnal patterns that you have of 12 hours and so forth. And so in those cases where you need to have those guarantees that you're not going to lose too much data, you couldn't do it. But you might consider applications where you really care about not losing what you did last week, and it's okay to lose what you did within 24 hours. And if that's the case, then you can make use of these diurnal patterns. But as a general cloud service, for example, Azure is intended for any application to go there and get deployed. People have determined that about 15 or 30 minutes is a delay that would be useful, broadly speaking. Right? Any more questions? Okay, well, thank you very much for coming to the school, and I hope that you guys enjoyed the lectures on behalf of everybody. Thanks.